The last part is, so we got this, right? So delta is defined so that this is equal to 1. That is why we can replace UE divided by x and divide by nu by 1 over delta square, right? And also in the Faulkner-Scaling solution, we set delta to be 1. We set the eta to be y over delta, right? Therefore, theta over delta is basically what is the momentum thickness in the eta coordinate. Okay. So for example, I'm just going to give an example. If theta is equal to 3 and delta is equal to 2, and we set eta so that height of 2 is actually eta equal to 1. So in the eta coordinate, theta is equal to 1.5. Okay, so this is what Thwaite defined as lambda, the parameterizing, the parameter that is going to parameterizing my T, or a scaled version of the skin friction coefficient. All right, is it clear? So now let's go into the Faulkner-Scaling solution to figure out what the relationship is. All right, let's do that. Okay. So what happens is I need to change the thin layer equation. Let me copy that. Call it Fs, Faulkner-Scaling. All right, we have this grid. Now, last time we coded up as a general thin layer equation, so we're advancing psi. In order for us to change this in to Faulkner-Scaling, we are just going to sweep over my alpha prime, right? Sweep over A. So close over all. Instead of making dig psi, I'm just going to make a list of A. So let's first, we know that if A is positive, we're going to get a very stable solution. When A becomes negative, the flow starts to separate, and at some point, we no longer get solutions, right? So let's swipe from positive backwards to -1. And we are going to break. We are going to just stop the iteration once we find out it is not converging. Okay, so I goes from 1 to length of A list. We no longer need this. We'll just say A is equal to A list of I. Okay, so here, in order to solve the Faulkner-Scaling solution, we just need the memory term to be 0, right? Remember what the memory term is? What should we do to set the memory term to 0? Yeah, right. All the parameters that goes to the g function.
C is 0 now.
C, make this equal to 0. Okay, so this is what we need to do to just solve the Faulkner-Scaling equation. Okay, so we make the C equal to 0. And all these are still the same, right? So we'll again just plot them to see if we get the Faulkner-Scaling solution. Okay, define the grid, we run it, initial guess.
Don't you still need a DC?
Do I still need a what?
A DC?
Oh yeah, right. That I just can put in an arbitrary value because whatever dC is used is going to be multiplied by C. So it doesn't matter now. Okay, and if this is 0, okay, so here I need to do something. I need to, after Newton iteration for 8 iterations, if it still doesn't converge, it's not likely to converge. So I'm going to compute the residual again, and if norm of residual is still greater than e to the minus 10, I'm going to break. Break. All right, so let's do that. Running. So here I get a family of profiles. Let's see what A did I. Okay, so the solution failed to converge for a equal to minus 0.1, right? So the last one it plotted is actually what? Is actually a equal to 0. So the Blasey's profile is the highest one. So we need some more precision basically. So let's go all the way to 0 and minus 0.01, 1 to minus 0.1. Okay, so let's try that. Did I? What did I get? No. So this is minus. Sorry. Let me do that again. Okay. So now, I think this one is probably the Blasey's profile. Now I get a bunch of more boundary layer profiles getting closer to separation. My last A, still it didn't converge at minus 0.1, which means the last one is minus what? 0.09. Yeah, that's right. And let's just add a bit more for fun. 09 minus 0.091 to minus 0.1. Okay. Did I? No. So let's run it. Did that work? Actually,
I don't think so, because the minimum is a little higher than
yeah, okay, minus 0.091. Which one?
I think you want to try minus 0.09.
Minus point. You mean here?
Yeah, because the minimum is higher than 0.091, right?
0.091. The minimum.
It's like 0.094. Negative
1. Oh, I see. So you're saying that didn't. Right. Okay. So you mean I should be doing that?
Yeah. You want to try that?
Right. Let's try that. Okay. So I get a few more ones before this thing stopped working. All right. I think the very last one should be exactly having a gradient of 0. So which we think almost got.
I think in Journal's book he said minus 0.0904.
Yeah.
Minus 0.0904. Okay, all right. So we are getting close to there. Cool. So here, our objective of doing this is so that we want to compute the relationship between lambda and t, right? So let's compute lambda and t respectively. So in order for me to compute lambda, basically I need theta square and a, which I already have. Okay, so let me compute theta. And previously we do have a displacement thickness, right? So let's compute a theta, which is very similar. So d is equal to 1 minus fp. So in this case, I want to compute the momentum defect, which is fp times 1 minus fp, right? All right. So this is still the trapezoidal rule for integration, right? And instead of displaying that, I'm gonna say like theta is equal to that. So that's my displacement thickness, and my lambda is gonna be equal to theta square times my a, right? Okay, so let me make a list of lambdas. List is equal to blank to start with, and I'm gonna say lambda list is equal to lambda list lambda. All right, so I'm adding 1 lambda onto the list. So that's good. We have the lambdas. We also need the corresponding t's, right? So t is defined as that guy. So du d-eta times theta over delta. So theta over delta is just my theta, right, in the eta coordinate. So du d-eta, what is?
Eta 0.
Yes, du d-eta at eta equal to 0. That's right. for skin friction coefficient. So I want to compute my T is equal to theta times FPP. You are right. That's easy. So FPP is FPP at 0, right? Yeah, right. Okay. So my T list is gonna be T list T, and I also make a empty T list. All right. So let's run this again. All right, get the same thing. I have my T list now. I have my where is my T list? T list and my lambda list. Okay, so let's plot it. Plot T list, lambda list. Let's show the points. All right. Okay, so that's good. We have the lambda and T. So lambda is a parameterization of alpha prime times theta square. So
The x-axis is T.
Yeah.
You plot it.
I plotted the wrong way. Yeah, sorry. I was saying lambda list should get to negative at some point. It didn't. So okay. So here's right. Okay. So on the left, it's the boundary layers that are thicker than the Blasius, right? That are closer to separation. On the right is boundary layer on the favorable pressure gradient, and we have the skin friction coefficient going in the vertical axis. So for boundary layer that is very close to separation, the skin friction coefficient is almost 0. For boundary layer profile that is very energetic, we have the highest skin friction coefficient.